Cosmology Supplement 5, Positive Curvature. Hello, welcome to this short supplement on positive curvature for the Expansion of the Universe course. The lecture script is available at a link given in the description of this video. Cosmologists believe that the curvature of our universe is either exactly zero, kappa equals zero, ordinary three-dimensional Euclidean geometry, or so small that it has played no role in the evolution of the expansion of our universe to date. For almost all of the main course, curvature was zero, a flat Euclidean universe. Here we will briefly cover attributes of a static, positively curved universe, but not its expansion characteristics. In reality, such a universe must expand or contract. It cannot remain static. Zero curvature is also called a flat universe, flat space, or a flat geometry. When you hear flat in this context, do not think that our three-dimensional space is some version of a two-dimensional plane. This meaning of flat is different than a flat plane. A flat universe is ordinary three-dimensional space that you always knew before you heard the phrase flat universe or zero curvature. This space is infinite. There is no maximum distance between 2 points. Parallel lines never meet. The sum of the angles of a triangle is 180 degrees. The circumference of a circle is 2 pi times the radius of the circle. Ordinary Euclidean space. The surface of a sphere is a two-dimensional surface with positive curvature. It is difficult to visualize a three-dimensional volume with positive curvature, so we will use analogies with the surface of a sphere. Consider ourselves to be tiny two-dimensional beings living on the surface of a sphere. The volume inside the sphere and outside the sphere are not part of our universe. Our universe is the surface only. If we set out in some direction and continue to travel straight in that direction, eventually we will return to our point of origin. Let's call that path the equator of our universe. There is a maximum distance between 2 points. For a three-dimensional universe with positive curvature, we would also eventually return to our point of origin, and there would be a maximum distance between 2 points. For the surface of a sphere, the area of the universe is finite but has no edge. For a three-dimensional universe with positive curvature, the volume of the universe is finite but has no edge. Let's take some given equator of our universe and consider two parallel lines perpendicular to the equator. On Earth, these would be longitude lines. The two parallel longitude lines intersect one another at the two poles that are equidistant from all points on the equator. Our parallel lines meet, unlike in a flat space, zero curvature. For a three-dimensional universe with positive curvature, parallel lines intersect, unlike a zero curvature space. Three non-collinear points determine a triangle. In flat Euclidean space, the sum of the angles of the triangle equals 180 degrees. For the surface of a sphere, and for a three-dimensional universe with positive curvature, the sum of the angles of the triangle is larger than 180 degrees. Here is an image of a triangle whose angles sum to 270 degrees. You can imagine one point as the North Pole and the two other points as being on the equator, 90 degrees of longitude apart. For the surface of a sphere, the sum of the angles of a triangle will be less than 540 degrees. In flat Euclidean space, there is no limit to how large a triangle we can make, no limit to the area. For the surface of a sphere, and for a three-dimensional universe with positive curvature, there is a maximum area that a triangle in that space can have. The circumference of a circle on the surface of a sphere is less than 2 pi times the radius of the circle. The distance in the surface of the sphere to the center of the circle in the surface of a sphere. For example, for the largest possible circle, the circumference is 4 times the radius along the surface, and 4 is less than 2 pi. The ratio of circle circumference to circle radius is a function of the size of the circle and the amount of positive curvature, whereas the ratio is a universal constant for flat Euclidean space. I hope this helps a little to imagine a three-dimensional universe with positive curvature. Finite volume, but no edges. A universe with positive curvature, containing radiation and matter, but no dark energy or cosmological constant, can begin with a hot Big Bang, expand at a decelerating rate, and then stop and then contract, ending in a hot, dense Big Crunch, or possibly a Big Bounce. But not if the universe contains a cosmological constant or most values of dark energy. A universe can also have negative curvature. We can visualize such a two-dimensional surface, but a three-dimensional volume we cannot visualize. This two-dimensional surface has a saddle point at the red dot. For a three-dimensional universe with negative curvature, every point would be analogous to the red dot saddle point, which we can't visualize. The space is infinite with infinite volume. Parallel lines never intersect, but neither do they remain a constant distance apart as we move along them. The sum of the angles of any triangle is less than 180 degrees. There is no size limit for triangles. An expanding universe with negative curvature, with radiation and matter but no dark energy or cosmological constant, can begin with a hot Big Bang and will end with a big chill. Our universe has curvature close to zero. It may be exactly zero or might be negative, and the universe infinite, or might be positive and the universe finite. However, our universe contains dark energy or a cosmological constant. If cosmologists are correct, our universe will not end in a big crunch. It will end with a big chill if dark energy W is between -1/3 and -1, or a big rip if dark energy W is more negative than -1 and remains so.